The principle of the universal mill is that the workpieces on the table may be addressed by a vertically oriented or a horizontally oriented spindle. Further, the combination of tilts and swivels available in the spindles and tables allow the workpieces to be addressed at a variety of compound angles. A milling cutter is a rotary tool with one or more cutting edges. Each edge removes a small amount of metal as it intermittently enters and leaves the workpiece. The variety of milling cutter types is immense. We'll examine only some of the most important cutter types together with the basic milling operations in which they are applied. Generating flat surfaces or flat surfaces with square shoulders is one of the basic objectives of the milling process. Face milling cutters effectively generate flat surfaces at high speeds with the spindle axis perpendicular to the work surface. Face mills range from about 3 inches to 2 feet in diameter. In face milling, the cutter body has multiple pockets to accept a variety of insert types. Metal is removed by the peripheral edge of the insert, and its bottom edge cleans up the work surface and produces the surface finish. Some face mills, called square shoulder mills, generate a finished milled shoulder that is square to the face they mill. Milling edges, shoulders, and grooves may use a combination of end, peripheral, and/or face milling operations. Edges may involve 1 or 2 surfaces, and the operation may be called edging. Shoulders typically have 2 surfaces. Grooves usually have 3 surfaces and may be closed at one end or open at both ends. Grooves may be cut on internal and external flat surfaces as well as round surfaces. Peripheral milling cutters have cutting edges on their periphery which are parallel with the axis of rotation. Peripheral milling is advantageous for long open slots and forms. End mill cutters are round shank tools with cutting edges on their periphery and end. The axis of rotation is perpendicular to the surface produced by the end of the tool. Its size is measured by diameter and cutting depth capability. Since end mills cut more with the teeth on their periphery than with the teeth at their end, they are susceptible to lateral forces. This makes them subject to deflection, which reduces the accuracy of the piece milled and can lead to tool breakage. Short, shallow slots are often done with end mills. Deep, narrow slots may be milled with an end mill, a thin slitting cutter, or a grooving cutter. Grooving or slotting cutters are generally more efficient than end mills in cutting long and deep slots because of their larger diameter and greater number of teeth. Chamfers may be produced with the chamfering end mill, which breaks the sharp edges of the workpiece with a 45-degree angle cut. Chamfers can also be generated using end mills, form peripheral milling cutters, long edge cutters, or face mills angled 45 degrees to the work surface. Pocket milling means the tool, an end mill or small diameter face mill, drills down to a certain depth and then mills out from there to create a shape, often with a flat bottom, called a pocket. Contour milling sculpts intricate curved forms in 3 dimensions and is essential for die and mold making. Contour milling is most commonly performed using an end mill, such as a ball nose end mill. Work holding devices in CNC milling include those standard vices and clamps already noted for work holding on knee mills, as well as devices specifically designed for machining centers. The T-slots of the machine table are still the primary means of holding work and work holding devices to the machining center table. Tombstones, commonly used on horizontal machining centers, come in a wide variety of configurations to hold multiple parts. The part program is written to machine all parts on the tombstone before shuttling it out of the machine. Setups on machining centers often utilize multiple vices in a variety of arrangements to get more parts done at a time. Multiple vices may be arranged on an indexing device to further expand the parts carrying capacity of the machine table. These often work in conjunction with rotary tables. Work changing represents another opportunity to get more machining done with less wasted time. Saving time by setting up fresh workpieces while the spindle is cutting is the goal. Work changing is accomplished in a variety of ways. A long machine bed may permit fixturing several workpieces with parts run sequentially. The pallet changer swaps fixtures holding multiple parts from the setup area to the machining area. There, the second set of parts is machined, while parts on the first are removed and new parts set up. Of the many accessories that may be used on machining centers, two are significant. One is the touch trigger probe. Together with appropriate software, the probe can perform measurements on workpieces before they are removed from the machine to determine if certain features are dimensionally correct. Probes are stored in the tool magazine. The second accessory is the tool presetting machine. It enables the machinist or tool room technician to accurately assemble tools and tool holders to the length and diameter assigned in the NC part program before placement in machining center tool storage. The selection of operating parameters in milling involves many factors. Only the most important will be included in this introduction. They are cutting speed, feed rate, axial depth of cut, and radial depth of cut. In milling, the cutting speed is measured in terms of surface feet per minute. This is how fast the edge of the tooth at the periphery of the cutter enters the work. It is a function of cutter diameter and spindle rotations per minute. Typical values for common materials may range from 40 to 1,000 surface feet per minute. The feed rate in milling is expressed in inches or millimeters per tooth. This is the linear distance a tool edge travels into the workpiece during one cutter revolution. It combines the effects of table motion, cutter diameter, and number of teeth on the cutter. A feed rate of 10,000ths of an inch per tooth is common. In milling, the table travel speed must be selected to achieve the desired feed rate. Table travel is not the same as feed rate. Table travel is expressed in inches per minute. There are two types of depth of cut, axial and radial. In face milling, the axial depth of cut is the distance the tool is set below the unmachined surface. Ordinarily, an axial depth of cut is selected to minimize the number of passes required to remove a given amount of material. The radial depth of cut is the width or distance of work surface engaged by the tool. Efficient milling also requires horsepower considerations, so that the milling cutter makes the best use of available machine horsepower. 1 horsepower can remove 1 cubic inch of steel per minute or 4 cubic inches of aluminum per minute. To mill an aluminum workpiece at the rate of 40 cubic inches per minute requires 10 horsepower. The power required for an operation varies with the amount of material removed, average chip thickness, cutter geometry, workpiece material, and speed. Let's re-examine the material contained in this videotape. It is automated on the machining center, and tool storage may range from 20 to 200 or more tools. The major operating parameters in milling are the cutting speed, which is the speed at which the tool edge enters the cut; the feed rate, which is the linear distance the tool edge travels in one cutter revolution; the axial depth of cut, which is the distance the tool is set below the unmachined surface; and the radial depth of cut, which is the distance of work surface engaged by the tool.